When we type the sine, cosine, or tangent of a given angle into our calculator, we get the ratio of how those two sides relate, depending on which ratio we're using. And it often is a whole bunch of decimal places in our calculator that we end up rounding off. If we need to give an exact value, so we don't want a whole bunch of decimal places, we can use special case triangles to leave that irrational decimal in radical form. There are two special case triangles, and if you can remember that the first one has a 1-to-1 side ratio. So whatever the length of this side is, this side here has the same measurement. Now, 1 is the easiest number to work with, which is why we tend to go with 1. If you can remember 1-to-1 side ratio of a right triangle, that's all the information you need to determine the missing pieces of information. If you ask yourself, okay, if we know this side length and this side length, could we find this side length? Well, we know we can find the third side of a right triangle using Pythagoras' theorem. Because this third side is my hypotenuse, I'm going to add the squares of the other two sides together and then square root that c squared to get the value of c. So I can calculate that third side. In terms of the angle measures, we know the sum of the interior angles in a triangle have to add up to 180 degrees. I already have a 90 degrees. I also know this is an isosceles triangle because those two sides are the same. Therefore, these two angles must also be the same measure. So if we take our 180 degrees in a triangle, take off that 90 degrees, these two are equal, so divide those two in half, and we know that each of those angles is 45 degrees. So knowing only those two sides allows us to calculate the remaining three pieces of information. Our second triangle is a 1-to-2 ratio, and we're comparing the short side to the hypotenuse. So if you can remember, the hypotenuse needs to be 2 units, and my short side here is this height of the triangle, and again, we know it's a right angle triangle. Ask yourself, if we know these two side lengths, can we calculate the third side length? And again, we can do that using Pythagoras' theorem. Now, because this is my c squared, my hypotenuse, I'm going to go this squared minus this squared, take the square root to get that third value. And we're going to, again, leave it in exact form. We know that third side is the square root of 3. And then, do you have enough information to determine those two angles? Remember, you can use your primary trigonometric ratios. You only need two pieces of information as well as that 90-degree angle. We now have that by knowing these two side lengths. So it doesn't matter where you start. However, the square root of 3 is not the easiest number to work with, so I would probably work with these two. And again, you can go about this a few different ways. I would probably take this angle. So I just used a theta to represent that, and then I've got that same theta here. So if I start with this as my reference angle, I know this side that I do know is my opposite, this side that I do know is my hypotenuse. The ratio that relates my opposite to my hypotenuse is the sine ratio. So in my calculator, by going second function sine, take the inverse of that, and then 1/2 or 0.5, we can determine that angle is 30 degrees. And then if this is 30 degrees, we know 180 minus 90 minus 30 gives us 60 degrees, or you can also use another primary trig ratio. This time you would use cosine, and you could get that 60 degrees as well. So there's more than one way to go about this. So if you can remember 1-to-1, 1-to-1, it allows you to calculate the rest. Short side to hypotenuse, short side to hypotenuse. And again, remember, the smallest angle in the triangle is always opposite your smallest side length. The largest angle in the triangle is always opposite your largest side length. So that helps you know which is 60 and which is 30. And you want those two special case triangles memorized. You use them so frequently, and you eventually will memorize them just from the amount of times you use them. Let's take a look at some examples of where we're given an angle as well as a trig ratio, and we have to get the exact value of how those two sides relate. So if you see an angle such as 45, you're going to think to yourself, okay, 45 degrees, that's a special case triangle. So you can quickly draw a sketch. I'm just going to refer to my one above here. If I start with 45 as my reference angle, we know the sine ratio relates the opposite side to the hypotenuse. So from here, we've got my opposite divided by my hypotenuse. And remember, we don't want to leave a radical in the denominator, so I'm going to rationalize it like we did with radicals, and then get the square root of 2 divided by 2. This is exact. If you type sine of 45 into your calculator, those decimals that you get will be the same decimals as when you divide those two values together. Similar, cosine of 30. 30 degrees, you know that's a special case triangle measurement. So go up to your diagram. This is 30 degrees. We know cosine relates the adjacent side to the hypotenuse. And again, if you want to write out that some old horses can always help the other animals, just to refer to as you're relating these, it might make it a little bit easier. Okay, so again, this is our adjacent side from that 30-degree angle divided by the hypotenuse. This is an exact ratio. We don't need to rationalize because we don't have a radical in the denominator. Tan of 60, again, 60 degrees, you clue in, that's your special case triangle. Tangent relates the opposite side to the adjacent side. So from that 60 degrees, this is my opposite, this is my adjacent. Set up your ratio, and then we don't need to write the denominator of 1, so we get this one. As soon as you go beyond 90 degrees, now you're into your angles in standard position. So you want to always draw your sketch out. So sine of 120, if we start here, remember we're rotating counterclockwise. So there's 90, and we know this is 180. So we're going to stop before we get there. So let's stop here. So I rotate 120 degrees, and again, this is not drawn to scale. That's my terminal arm of that angle. I know if this makes up 180 degrees, 180 degrees minus 120 gives me a reference angle of 60 degrees. As soon as you see a 60, a 30, or a 45, you're going to have little bells going off in your head because that clues you in that's a special case triangle. We can get an exact ratio. So now, similar to what we did previously, I'm going to draw my right triangle here. I'm going to use my 60 degrees. We know sine is comparing the opposite side to the hypotenuse. So this is our ratio. We don't need to rationalize because we have a whole number in the denominator. All of these ones today are going to contain special case triangle angles. So I'm going to get you to try those last ones. Again, you can draw your sketch, refer to those two diagrams above. Do we have a 45, a 30, or a 60 angle? If so, we can give an exact ratio. All right, so you're going to pause me. I want you to try those and then come back and we'll see how you did. I wanted you to try those remaining 4 examples on your own because I wanted you to see if you could get the right ratio values. And then there's a second piece you also have to keep in mind is whether or not those ratios will be positive or negative. All right, so going back to the fourth one, we know 135 degrees is going to be between 90 and 180. So I can draw my terminal arm there. There's my 135 degree angle of rotation. I know that my reference angle is 45 degrees. And ding, 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 that's a special case triangle. We know if this is 45, this is a 1-to-1 side ratio, but take a look at your axes. This is a positive y value. I'm above the origin. However, because I'm to the left of the origin on the x-axis, this is a negative 1. Remember, your radius will always be positive. You can't have a negative distance or length value. So because cosine is so if I use this as my reference angle, adjacent divided by hypotenuse, that gives me a negative 1 over root 2. So then when I rationalize, I end up with negative square root 2 over 2. And again, go back to the cast rule. And actually, let's maybe just quickly draw this out here. So I know cast, if I terminate in quadrant 2, only the sine ratio is positive. Because this is cosine, I know I have to have a negative ratio. Same thing with this tangent one. I'm going to draw my angle of rotation. I know 150 degrees is between 90 and 180, so I terminate in quadrant 2. I know at quadrant 2 only the sine is positive, which means tangent must be negative. This is a negative x value. This is a positive y value, and again, my radius will always be positive. So if this is 30 degrees, remember, the short side is opposite my shortest angle. So put the 30, we know this is going to be 1, and then we can fill in those remaining sides. This is my 60 degree angle, so that root 3 is opposite from that. All right. Sine of 225. So now when I rotate, I'm going to hit 90, 180, and I'm going to keep going. So 225 degrees will terminate between 180 and 270. So I terminate in quadrant 3. We know only tangent is positive in quadrant 3. Sine is going to be negative because this is my negative x-axis and this is also my negative y-axis. So when we fill those in, we're going to have the so if I take my 45-degree reference angle, my opposite side is -1, divide by my hypotenuse, which is the square root of 2. The easiest way to do this for most people is don't worry about the negatives in the beginning. Get those values in there. And then once you write the values in, then say, okay, is this negative or positive? Is this negative or positive? 300 degrees, we know, terminates in quadrant 4. It's between 270 and 360, so this can be 0 degrees if the two arms of the ray are on top of each other. If we make one full rotation, it's also 360 degrees. So I'm stopping 60 degrees short of 360 because our angle of rotation is 300 degrees. 60 degrees, ding, 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 is a special case triangle. So we know if this is 60, actually, let's fill in here. This is a right angle triangle. So if this is 60 degrees, I know this is 30 degrees. Opposite 30 is my shortest side. That's the 1 to 2, and we can calculate that third side. This is the positive x value, negative y value, so I can fill in my negative sign. Cosine, we know from our reference angle of 60 degrees is the adjacent side divided by the hypotenuse, so we just end up with a 1/2 ratio. Another type of question you're going to see is where you're asked to determine all angles of rotation between 0 degrees and 360 degrees. Sometimes you see a theta here. In this case, we're using an A because in each of these examples, they're using capital A to represent the angle. This is similar to what we did before. So in grade 10, you just go second function sine and then enter that ratio to get your angle. We're now going to keep going past that 90 degrees and we're going to do all angles within that full circle. So we start the same way. We get that reference angle by entering the taking the inverse of that ratio. And then once we have that, we're going to think about the cast rule and we're going to say, okay, my ratio is positive. Sine is positive in quadrant 1 and quadrant 2. I know that my arm is going to terminate in those two quadrants. So if you draw yourself a sketch, this is the reference angle, which remember has to be between the x-axis and the terminal arm. So there is my x-axis, there is my terminal arm, that's my 30-degree reference angle. Or in this case, that just is 30 degrees because we're quadrant 1. Here, this is my x-axis, this is my terminal arm. That 30 degrees has to go there. And so then we can see in quadrant 1, the reference angle is just the angle of rotation. In quadrant 2, if this is 30 degrees, we're going to go 180 minus 30 degrees means that we have a 150-degree angle of rotation. So those are the two angles between 0 and 360 degrees given that ratio. Same thing for the next one. Use your calculator. You're going to go second function cosine, 1 divided by the square root of 2 to get your reference angle. Once we have that reference angle, we're going to say, okay, cosine is positive. This is a positive ratio. We know cosine is positive in quadrant 1 and quadrant 4. So again, in quadrant 1, that 45-degree reference angle is just my angle of rotation. In quadrant 4, we can see we stopped 45 degrees before going a full 360 circle. So if we go 360 minus the reference angle, we get the angle of rotation. So from here all the way around to the terminal arm, that is a 315-degree angle. If you have a negative ratio, like we do in the third example, you're going to say, okay, this is tangent. When you put this into your calculator, remember, don't put in that negative. It throws some calculators off. So you're just going to go second function tangent 1 equals, and that will give you the reference angle. Then you're going to say, okay, where is my tangent ratio negative? So it's going to be negative in this quadrant, and it's going to be negative in this quadrant. The only quadrants it's positive in are 1 and 3. So we want where it's negative, which is going to be the remaining quadrants. Draw your terminal arm, and again, remember, my 45-degree reference angle has to be between the x-axis and that terminal arm. So that's 45 degrees. If we take that away from 180, we get the 135-degree angle from here to here. And then The second one is that 315 degrees, which we get by taking 360, subtracting 45, and that is a 315 degree angle of rotation. So in each of these cases, you're going to want to draw out, well, you're going to want to use your calculator, determine that angle of reference, and then figure out where is that ratio either positive or negative, depending on what you're given. And from there, are we adding or subtracting that reference angle to what, depending on the quadrant. So eventually you should get to a point where you don't necessarily need to draw the whole thing. Even this is enough just to help people visualize where your arm is going to be. So I'm going to get you again to pause this. I want you to try those last few examples there and see what you get. And then when you're done, come back. And how did you do? The last thing we're going to do is determine the angle of rotation as well as the trigonometric ratios given a point on the terminal arm of an angle in standard position. My first example has a point of 1, 1. I know that the first value is my x-coordinate, and it's positive. My second value is my y-coordinate, which is also positive. So I'm going to go on the positive x-axis to 1 unit. I'm going to go up on the y-axis 1 unit to positive 1. So there's my point 1, 1 on the terminal arm. Once we have that, we're going to take a look and say, okay, this we can draw in our triangle here to create a right angle triangle. I'll put my little right angle in here. And then again, those bells, ding, 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 are going off. If you have a 1-to-1 ratio, that's a special case triangle. So we know if this is an isosceles triangle, both of those angles are 45 degrees. We only want this one. That's our reference angle. Now, because we have a reference angle of 45 here, I know that my angle in standard position is just that reference angle. So my angle of rotation is 45 degrees. Now my three primary trigonometric ratios, again, I'm going to want to fill in those, I know those two sides, I'm going to want to fill in that third side there. From my reference angle, sine is opposite over hypotenuse. So that's that 1 to 2, rationalize the denominator, and there's our sine ratio. Cosine from this angle of reference we know is adjacent divided by hypotenuse, so that's that ratio, and again rationalize to get to this. Tangent of this ratio we know is opposite over adjacent, and 1 divided by 1 we can simplify down to 1. In the second example here, this time we have a negative x value and a positive y value. So on my x-axis I'm going to go over to -3, the square root of 3, and I'm going to go up to positive 1 on the y-axis. Again, -√3 and positive 1, those two sides are the sides that relate in our special case triangle. I know this is going to be a 30-degree reference angle because it's opposite from my shortest side. I also know that this third side is a value of 2. The 1 to 2 triangle is our special case triangle. I know that my reference angle is going to be 30 degrees. Because again, if we go back and take a look at those examples, if we go back and take a look at the top of those pictures, we can see that 30 degrees is across from that shortest side. And so then because I'm terminating in quadrant 2, I know that I rotated to here. So it's going to be 180 degrees minus that 30 means my angle of rotation is 150 degrees. So the sine of that 150 degree angle, again, if you look at your triangle, this is my reference angle, this is my opposite divided by my hypotenuse. Cosine of that 150 degrees is the adjacent side divided by the hypotenuse. And tangent of that 150 degrees is the opposite side divided by the adjacent side. And again, we're going to rationalize to get rid of that. And I also don't want to leave a negative in the denominator. So we're just going to move that up to the top there. All right, try the last one. Pause me and see what you can get with that one. I already have the work here. And then come back and see if that works out for you. And when you take a look at this, we have a positive x-coordinate and we have a negative y-coordinate. So I'm going to be at positive 1 on the x-axis. I'm going to be at negative the square root of 3 on the y-axis. And again, we know those two are sides in our special case triangle, the third side being 2. Now, I know that 1 is my shortest side. The 30-degree smallest angle has to be across from that. So I just put this in here to help me get set up, meaning my angle of reference has to be that 60 degrees. It's always the angle between the x-axis and the terminal arm. So it's that 60 degrees I'm going to use. So if I'm rotating from here all the way to here, I'm 60 degrees short of a full circle, which means my angle of rotation is 300 degrees. The sine of that 300 degrees, again, use that reference angle, is the opposite side divided by the hypotenuse. The cosine is the adjacent side divided by the hypotenuse, that 1/2. The tangent is the opposite side divided by the adjacent side. And again, it's okay if I have a square root in the numerator. I can just leave that. I don't need to write the 1 in the denominator. All right, and if you would like some extra AP for today, these two are just for fun. I know you're all thrilled to be trying these, but if you want to try some, these are just extra for fun. Give those a go, see how you do, and I will be back in a second with the correct answers. Okay, these last two were just purely for enjoyment, if you're looking for something to do these days. This time we're given a sine ratio, and again, I'm going to ignore the negative sign when I put this in my calculator to get my reference angle, which I know is 60 degrees. We know the sine ratio is negative in quadrants 3 and quadrants 4. So I can draw those terminal arms in, and again, I know that that reference angle between the x-axis and the terminal arm in each case is going to be 60 degrees. I know sine is opposite over hypotenuse. So from this reference angle, my opposite side is that √3, my hypotenuse is that 2. And then watch your negatives. This could have been potentially moved to the numerator. So in this case, we know we're on the negative y-axis and the negative x-axis. So now we can fill those in. Similarly, on this side, we have that reference angle. Opposite is that √3. Hypotenuse is that 2, and then take a look. We're at the positive x scale, we're at the negative y scale. We are looking for the values of cosine. We know cosine from this reference angle is adjacent divided by hypotenuse. That gives us the first ratio. The second one, again, from our reference angle, we know cosine is adjacent divided by hypotenuse. That gives us the second ratio, a positive 1/2. When you go to put this in your calculator, you're going to notice this is not values we see in a special case triangle. We're going to end up with an irrational number, and that's okay because it doesn't want us to get the angle of rotation. So what I can do is say, okay, tangent is positive. I know tangent is positive in quadrant 1 and quadrant 3. So let's try to draw this out and see what we get. I'm going to draw my terminal arm here, and I'm going to draw my terminal arm here. And again, these are not to scale. If this is my reference angle, I know in tangent we have an opposite side of 2 and we have an adjacent side of 5. Well, if I'm looking for the sine ratio, I'm going to need to calculate that hypotenuse, which we can do knowing two sides in a right angle triangle. We can use Pythagoras' theorem. So I can calculate that hypotenuse to be the square root of 29. And now the sine of this angle, I know, is the opposite side divided by the hypotenuse. And then again, just rationalize to get that radical out of the denominator. The quadrant 3, again, here's my reference angle. Now I know tangent is opposite divided by adjacent. But I'm at the negative y-axis and I'm at the negative x-axis. So once we get the values filled in, then you can go in and put the signs in. I'm going to, again, recognize that this is my hypotenuse. It's never going to be negative because it's a measure of length. And then to get the values of sine, we can say, okay, from this angle, sine is opposite divided by hypotenuse. And so that gives us our last ratio, just for some added fun for you guys.